All right. Okay. Welcome to the DDPS seminar, everyone. Let's go over some logistics. First, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. Finally, the talk today will be recorded. All right, that's about it. Now, let me introduce our speaker today. It is an honor to host Peter Banner, who is a director of Max Planck Institute of Dynamics of Complex Technical Systems, Magdeburg, Germany. Since 2003, he has been a professor for mathematics in industry and technology with the TU Chemnitz. Since 2011, he has also been an honorary professor with the Otto von Guericke University of Magdeburg, Germany. He is a Scion Fellow, class of 2017. He received a diploma in mathematics from the RWTH Aachen University in Germany in 1993. From 1993 to 1997, he worked toward the PhD at the University of Kansas, Lawrence in US, and the TU Chemnitz, Zwickau, Germany, where he received a PhD in mathematics in February 1997. In 2001, he obtained the habilitation in mathematics from the University of Bremen, Germany. He was an assistant professor with the University of Bremen, Germany from 1997 to 2001. After spending a term as a visiting associate professor with the TU Hamburg, Germany, he was a lecturer in mathematics with the TU Berlin from 2001 to 2003. All right, his research interests include scientific machine learning and computing, numerical mathematics, systems theory, and optimal control. A particular emphasis has been on applying methods from numerical linear algebra and matrix theory in systems and control theory. Recent research focuses on numerical methods for optimal control of systems modeled by evolution equations, model order reduction, Krylov subspace methods for structured or quadratic eigen problems, and using machine learning for identifying dynamical systems. Research in all these areas is accompanied by the development of algorithms and mathematical software suitable for modern and high-performance computer architectures. Today, Peter will present an interesting topic, which is identification of nonlinear dynamical systems from noisy measurements. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton by asking one random question as usual. Since Peter is from Germany, what is your favorite things to do in Germany? After answering that question, you can, stage will be yours.
Visiting football games of Bayern Munich.
Okay, so you're the fan of the Bayern Munich. Okay, that's awesome.
So I had a good night last night for those who are following.
Oh, okay, they won. Okay, yeah. Nice. Okay, the stage is yours.
Okay, thanks, Yang-Su. Thanks for the nice introduction. And I'm not sure whether I should say thank you for raising the expectations so high as you did. Yeah, this talk is joint work with Pavan, who spoke in this seminar earlier this year. In a way, it is a continuation of his work. And I should say that Pavan did most of the technical work here in this what I present today, and he's around. So I hope he can ask the nasty technical questions that will come up at the end of the talk, certainly. But I will do my best to explain the material and to show you what we've been doing. Just move this speaker window a little bit so I can see my own screen better. Okay, so before I go into the talk, I would like to acknowledge some research funding that was supporting this research partially. The one is from a research training school of the German National Science Foundation, the DFG, which is called Mathematical Complexity Reduction. And the second is the Big Max. It's a Max Planck Research Network on Big Data-Driven Material Science. It's not so much related to the topic of the talk, but when we started this network, that dragged me into looking into machine learning more than we did before that. And Pavan was hired in this network as a postdoc after he graduated, and he has been on the driver's seat on machine learning in my department for the last 3 years. So today's talk is following this line of research. So I think the identification of dynamical systems from data is something that has inspired generations of researchers in systems and control theory. I should have actually added a slide here. Early works you can find already in the 1960s. Interestingly, you can find even a textbook from 1996 about using artificial neural networks for identifying dynamical systems from Jos van der Walle and Bart Moore and a third author whose name I just missed. But of course, in 1996, they did not have the machinery, the hardware to make use of really deep neural networks. So this topic was a little bit neglected for 20 years and received renewed interest since deep learning and machine learning as a more general area of research has gained so much popularity. The age of discovering nonlinear systems is, I think, just blossoming, even so there is a lot of literature and research and literature available from the last 3 decades, and there's software and so on, but a lot of challenges remained. And one of the challenges is how to deal with noisy measurements and how to provide data for the training and so on. So we will focus a little bit on these topics and try to add a few bits and pieces to the tool set of methods to identify nonlinear dynamics from measurements. Okay, so this is the outline of the talk. I will just briefly introduce the topic. I think talks in this direction have been given quite a bit in this seminar series, so I will not start with Adam and Eve, but basically start where Pavan left a couple of months ago. We will then formulate the working hypothesis of the sparse identification of nonlinear dynamics approach, the SINDI approach that was popularized by Nathan Kutz and Stephen Brunton a couple of years ago. And we will focus on one issue with this approach and suggest a new variant, which we call Runge-Kutta SINDI. It will become obvious why it's called that way. I will give you some extensions of the approach, or I will show how it works on several benchmark examples that are also used in the PNAS paper by Nathan and Stephen, and some other examples as well. And we'll also look at a few extensions of the approach. And in the end, we will add a higher level of noise, and that means we will have to use a slightly different approach, but it's blended into this talk because it also is based on using the same Runge-Kutta scheme that we use in the Runge-Kutta SINDI. All right, so just as a teaser, dynamical processes are omnipresent in computational science and engineering. You see 3 pictures of typical processes on the right. On the bottom, you see a CFD simulation around a turbine. You see microcircuit or nanocircuit in the middle. And at the top, this is actually an example from our own institute, where we also have engineering departments. We have 4 departments. I'm the mathematician, and then there are 3 engineering departments. And this is an example of batch chromatography, which is a nonlinear coupled system of partial differential equations describing the separation of two products from a liquid. Will not use this example here in this talk, but I have used it quite a bit on model reduction talks that we gave on reduction. It's an interesting problem, I should say. Assuming now that we do not have a model for the process that we are studying, but we assume that we can measure any of these things that we have here. For instance, you know what you feed into A and B, and you know what you measure, what you extract at the end. So this is the mixture, and this is then the separated liquids that you can measure at the end. You can take a time series on how much of the liquid of the A you get at a certain point, how much of the B. You want to find the mathematical model. Because why do you want to do that? You want to design a controller to attenuate disturbances of your potentially optimized process. If it's not optimized yet, you may want to optimize it with mathematical optimization, which also, again, needs a model in order to apply optimization algorithms. And you may also want to be able to predict the future behavior, for instance, for the turbine, if it's a turbine of your Boeing 747 that we are hopefully all using soon again. You want to know when it breaks, right? And you want to know that in advance to take measures to land safely. So these are the motivations of finding models from data of dynamical systems, some of the motivations. So the general setup we will be using in this talk mostly is just an autonomous nonlinear dynamical system with time derivative denoted by x dot and a vector field describing the right-hand side as f of x. And then you can find in the literature, of course, many neural network approaches to provide the output or the dynamics of the system from measured data. And there's the current neural networks being used for this long short-time memory networks that roughly require no prior knowledge on the physics of the process. They are not always parsimonious, as you would like them to be used in this in control and optimization. You don't get governing equations directly from them. I mean, it can be worked in, and this is basically where what I'm talking about converges to these approaches, or with these approaches also. And they do often not well generalize outside the area where they are trained. That's the good old generalizability problem of neural network approaches. So we are following here the path of making some hypothesis that allows us to identify actually model equations. And this path is essentially what is known in the community nowadays as SINDI, as I already said, popularized by Nathan and Stephen, and added with a lot of features and so on. The basic idea is that we assume that the function f, the vector field f, can be described by a small number of terms of nonlinear functions. And the idea is now to build a dictionary of candidates from which we pick terms that at the end of the day give us an f that can describe the data that we have measured. And such a feature dictionary, which we will call capital phi of x, could look like that. So it will have polynomials up to a certain degree. So this would be all the polynomials that have degree 2, as an example given below. if our state, we have n states, so the state vector x has n components, the possible polynomials would be x1 square, x1, x2. X2, x1 is the same, so it would not be added here. X1, x3, x1, x4, and so on. And then you go all the way up to xn square. You do the same for cubics, quintics, quartics, whatever you want to, what you think you need. There's a little bit of that's actually the shortcoming of this approach. You would have to have an idea which kind of terms you need in order not to make the dictionary too thick, basically. Exponential functions, trigonometric functions, you put in what you like. And then the vector psi is the vector that picks the features from your dictionary that at the end of the day define your function f that you need to describe the dynamics. So the challenge now is, first of all, you have to define your dictionary. And I assume that this is given in some sense. And we want to compute the vector psi. So this is basically, this idea was brought into the engineering world, I think, maybe first in the paper by Baumgart-Lipson in 2007. And it was formalized and extended in the SINDI work by Brunton, Proctor, and Katz, appearing in PNAS in 2016. So how do we get the psi? We compute it by solving this minimization problem, which already shows where we have the difficulty in this approach, or one of the difficulties is we need data for the derivative x dot. And well, there was a remark that the Lipson paper has a different approach. Of course, the approach is different, but I think it's an idea to reverse engineer a function from data and doing that with a number of features. Let's keep it on this basis, yeah. Data, so it might be, for several reasons, might be difficult to get good data for the derivative. Numerical differentiation could be used, I mean, of the data, based on the data that you have in your time series, but we know that this is often does not give good results. Also, of course, the construction of the rich enough feature dictionary allows efficient, is important, and there we hopefully have some idea on the physics that we want to model, some domain knowledge that helps us to find a good dictionary, say. And for the derivative data, we want to suggest an approach that is based on using an idea from numerical analysis, that we all know from our first class in numerical analysis, that can be used to solve ordinary differential equations, the Runge-Kutta scheme. But here it's not used to solve, but it's used to find a different minimization problem that does not require to find derivative data from the time series that we have available. So just as a short recollection of your undergraduate years, what is the Runge-Kutta scheme? Given a differential equation in the form that we want to basically identify setting, and given we have a function value of the solution x at a time ti, we want to predict the function x at time ti plus 1. And then the Runge-Kutta scheme is just one of many methods that we learn all in undergraduate school. It's one of the explicit methods that does not require solving nonlinear systems to compute x of ti plus 1. It's just using a weighted sum of the vector field evaluated at specific locations. I think often these are called computing the stage derivatives. So usually you compute basically the vector field at points between, or you approximate the vector field at points between ti and ti plus 1. Here's how it looks like precisely. Hope everybody remembers. It's this weighted sum of these stage derivatives, where k1 is just the function evaluated at ti and so on. And then you get an approximation of x of ti plus 1. It has an error that is behaves like h to the power 4, so this is nice. It doesn't have very good stability properties when solving stiff differential equations, but this is not the focus here. The focus will be to make use of it within the SINDI approach. The notation that we will be using for this formula here will be this capital F with the RK4 identifying the fourth order explicit classical Runge-Kutta scheme. The issue is here, of course, we cannot apply it here in our context to the data because the function f is not known. This is what we want to identify, right? So cannot use this scheme per se, but we know that we have our working sparsity hypothesis. So we apply the Runge-Kutta scheme for our ansatz, phi of x times psi, times the selection vector that selects the features from the dictionary. So we put in our working hypothesis, or component-wise, it looks like this. And so we would get in component-wise this equation, and this is what the standard SINDI approach would now use if derivative information is provided. So, but we want to use the RK4 scheme, and this means we use we use the following. We with the help of the RK4 scheme, our data, our time series data would have to satisfy this equality if it were produced by RK4, but it's usually not the case. We don't know how it is provided, but we know that the RK4 scheme would be a good approximation of the time evolution, at least if the step size is small enough. Okay, so we insert now in our RK4 formula our representation of the function f that is represented now by our dictionary and our selection vector. And we make the evaluations in the RK4 scheme based on the sparse, hopefully sparse, if the sigma vectors are sparse, representation of our function. And this would lead then in a visual way to a procedure like that. You start with, you have input data, that's your state at time ti. You feed it into your representation feature map representation, and then apply the necessary steps in the Runge-Kutta schemes to get at the output x1. Now, of course, we don't know the sparse vector, the selection vector psi. That's what we want to compute. So this now gives us the following regression problem that looks like this. Yeah. So we have the task to determine the sparsest possible psi vectors minimizing this problem, so that the data would follow the Runge-Kutta 4 evolution. As we all know, this is a compressive sensing problem that is NP hard to find the L0 norm minimizer. So we do the usual thing, we do the L1 norm relaxation by appending this relaxation term. And we know that this often even gives you the sparsest possible vector under the RIP property that we may not have here. But at least we get something close by. What we then do is we use the same sequential thresholding algorithm that was suggested in the paper by Stephen Brunton and Nathan Kutz, just applied now for this regression problem, sensing problem that we have formulated. It's slightly differently from the original paper, where you would have to use the derivative information that we do not employ. So here's the thresholding algorithm. We solve the Lasso problem 1, find the indices that are below a certain threshold, lambda, set them to 0, then with the indices set the components of the sigma vector set to 0, we solve the optimization problem again, and loop until the error is small enough, or until the convergence is established, so that we do not get any improvement. And then we take these computed selection vectors and pick the corresponding elements from our dictionary to define the function. So this is basically the procedure. So it's similar in a sense than what is done in the standard SIMD, just we have replaced this optimization problem from the original SIMD approach, but this one based on the Runge-Kutta scheme. Still a nonlinear, non-convex optimization problem. For the computation, we use gradient-based optimization. For instance, Adam is now popular in the machine learning days. We use for the gradient computation approach implemented in PyTorch. For finding lambda, that's also, I think, already suggested in the SIMD paper. We use a cross-validation approach. And let us see how this works. The first example is from the original paper. It's a cubic oscillator, a cubic damped oscillator. It's a two-dimensional, very simple system of differential equations. So it has the only terms in the right-hand side are all cubic. The feature dictionary that we use in this test contains all the polynomials up to degree 5. And we compare our approach with the standard SIMD approach. And this is what we get. So this is these are basis of the solutions of the clean data in red, and the standard SIMD in dotted line, and the our approach in the black connected line. And you see that for small time series data with small step size, I should say that the training data was obtained with adaptive ODE solver of order 4-5. So it's not at all related to the Runge-Kutta scheme that we use in the identification. You see that for small enough step sizes, both approaches are able to identify the dynamics quite well. But if you make the step size large enough, you can see that the standards in the approach becomes unstable, while we are still able to to approximate the dynamics quite well. And you can see the reason in this table let's just look at the last row where we have the largest step size used. We are still identifying a model with only cubic terms in the right-hand side with our approach, and a little bit of error in the coefficients compared to the original model. But in the standard SINDI approach, using the same threshold values in the iterative thresholding, does also insert quadratic terms and also a quintic term here, for instance, and here into the model. And this, at the end of the day, leads to the larger errors. Already for the next smaller step size, 0.05, we see that SINDI does identify terms in the right-hand side in the vector field that are not present in the clean ground truth model. All right, so that was happy to see that our approach was able to deal with this. We also tested Fitzhugh-Nagumo, which is an example that we often use for testing nonlinear model reduction method. It's a very simple and basic model for the spiking of a neuron in the brain. Here it's even a simplified version of that. In a model reduction, we often have the first equation spatially distributed, so that is a PDE. But here you have a cubic term in the original model. Again, the feature dictionary that we use contains the polynomials up to degree 5. We do the same comparison. We see again that for the largest step size, SINDI starts to deviate from the ground truth, while we are still able to follow the ground truth very nicely with the AK4 or AK-SINDI approach. Again, you see that for the larger step sizes, SINDI identifies terms that are not present in the original model, while we get basically only those terms that are also present in the ground truth. Okay, so extensions, we can add parameters to our description of the dynamics. So we play a little trick here that we augment our states by the parameters to define a new state variable x mu, and then we append also the right-hand side, because this is for parameters that do not vary with time, so their time derivative is 0. So the augmentation of the vector field is easy, and this is not something we would not need to identify if we do this immediately. And then we also add polynomial, or say features of mu in the dictionary. We test this here for an example that is also often used in the SINDI and sparse identification literature, as the parametric Kopf normal form, which exhibits bifurcations depending on the parameter mu. Here we look at data that we corrupt artificially by a very small, tiny fraction of Gaussian white noise to see how robust this is with respect to little perturbations. Dictionary this time, we only added polynomials up to degree 3. And we see that AK-SINDI is also able for the on the test set of the parameters for which we have no data collected, to reproduce the solutions in phase space quite nicely. Again, we see that the AK for SINDI discovers a more parsimonious model than the standard SINDI approach, and there's also again a few terms here in the standard SINDI approach that are not present in the ground truth. So our approach shows a little bit of advantage here as well. We can also do rational functions on the right-hand side, which is important in this example that I showed you from the process engineering, from separating of chemicals. You usually have rational terms in the model descriptions. So if we have data, we would expect that we want to identify also rational functions. Now, if your ground truth, for instance, would have such a rational right-hand side, you would have to put that into your feature space to identify it essentially, or this term, which of course, as you don't know what the rational functions involved in the right-hand side, you cannot do, and you cannot do this for many values of a parameter, for instance, in front of the x term here in the denominator. So what we do in this case is we expand our approach to allow for two sparse selectors, and we apply them in the denominator and in the enumerator, so that we have two different representations, as one would do also often in other computations with rational functions. So we would say, if we assume that this is a rational function, we would identify a sparse polynomial in the enumerator and the sparse polynomial in the denominator. And we have tested this for the Michaelis-Menten kinetics equation, which in the easiest form for an enzyme dynamics looks, for instance, like this. And we use different initial values to get the training trajectories. And then we learn a model with our rational Akar-Sindhi approach. And what we show here is, so this is the range where the initial values of the training data were, and this is outside the training range. So these are the initial conditions that we have not trained our model on, and we can see that for this simple example, at least, we get a generalizable model from the data that works well outside its training regime. Okay, so far, let's see where are we with time. Okay, we have presented, added a little bit of a different approach to deal with the problem of using derivative data in the Sindhi approach. The scheme that we propose does not require any estimate of derivatives. Of course, as with all dictionary learning approaches, the quality depends highly on the quality of the dictionary. And we also see that this approach, or we saw it at least in one example, behaves rather robustly in the presence of small noise. Up to 5%, I think. We saw in the examples that it's working still quite well, but beyond that, we see that there's an issue. And this approach will also not work anymore. So we looked into this problem more recently. This is rather new work that was just, I think, submitted last week or the week before to the archive. And to deal with the noise, we make now use of ideas from neural networks, but combine it again with the RK4 scheme that we have been using in the Sindhi approach as well. So this connects the two approaches. So how is this done? The first step is to learn to find an implicit representation of our data. This is done by a straightforward feed-forward neural network that takes time as the input and that takes the state at the as the output. And then we compare it to the noisy measurement as a loss function, and we learn essentially the implicit representation. So this should filter the noise. Of course, we need to regularize because otherwise the network would overfit. And we do this again with a Runge-Kutta scheme. So we again know that this is a time series that comes from a differential equation, and the Runge-Kutta scheme is able to approximate the time, the evolution of a dynamical system. So the time series should, and the output of the Runge-Kutta schemes should be close by. And so we filter essentially this data again by requiring that it follows the evolution that the Runge-Kutta scheme would predict. Of course, for that, we also need the right-hand side for our dynamical system in order to make use of the Runge-Kutta scheme. And this, because we don't know anything else at the moment, we also represent by another neural network. So the whole approach looks like that. We take the noisy time series data. We find an implicit representation for this time series using this first neural network. Then we run this through the Runge-Kutta scheme, which requires another neural network to represent the nonlinear, the vector field, the nonlinear dynamics, the right-hand side. And yeah, and at the end of the day, we get an implicit representation of the denoise data as well as of the dynamics. And how is the learning process controlled? It's controlled by the loss function, so that our implicit representation should fit the data. At the same time, the denoise data should follow the dynamics that is behind the process, and that we get from the Runge-Kutta scheme applied to the other network whose parameters we call phi. So there's parameters, I think, theta for the implicit representation of the data and phi for the dynamics. And we also include the gradient loss here in the loss function. We can do that because we know that the time derivative of our states, this would be represented by the neural network we learned for the dynamics. And as we have the implicit representation of the data by this feed-forward neural network, we can use automatic differentiation to get derivative data for this implicit representation. So we can evaluate this loss function. And so we have, of course, these two weighting parameters to get this representation. So with that, we hope to be able to find a representation of the dynamics of a time series for noisy measurements. And I should mention here that there's no need for a uniform mesh on which this time series is collected. It can also be sparsely collected at varying time distance. So there's no assumption on the time criteria. So here we test again this example for the Fitzhugh-Nagumo that we already saw. We collect the data for a certain initial condition and corrupt it by different noise levels. And what you see here is, let me see. So it's just covering my slide here. So this the top row is for the noise level 5%, so little noise. You see in green, that there's a little bit of variance around the ground truth, the denoise, the clean data. And you see the denoise data. And here you see also in phase space noisy and the denoise data. And you see the vector field that we identify with this neural network approach. And then we crank up the noise level up to 40%. So you see basically the noisy data in phase space gives you a point cloud from which you cannot see much. But with our approach, we are able to find a model that produces these limit cycles in the phase space that we know exist in the Bitsu-Nagumo model, even for this noise level of 40%. Okay, so this brings me already to the end of the talk. What we have, no, it's not quite the end. Sorry, there's one more point. This approach that I just demonstrated here for these simple ordinary differential data obtained from ordinary differential equations could be extended if we make the assumption that the data that we measure is would be modeled or would come from a model that would require a partial differential equation. So this is where we are currently at. Here we also have the spatial to take the spatial coordinates that we then assume that they exist in a PDE model as inputs for this implicit network in order to denoise the data. Oops. The neural network defined the vector field here was modeled then using a CNN. That also makes use of the spatial information. And this is relatively new thing that if you have a question on how this is done exactly, Pavan will be happy to answer. So you see this approach at work for the Burgers equation here. You see initial data, that datum that we often see in examples, a strong front in the initial condition that fades out with time. Here we have noise level 5%, so this is not so much. And here we go up to 20%. You see that the measurements, it looks already quite rough for this level of noise. And we see that the denoised solution here, denoised data, it shows a little bit of wiggles down here, but the main features of the solution are very well recovered. Okay, this is now the end of the talk. What we have done is we have blended SIMD with a Runge-Kutta scheme to avoid derivative estimation from the time series data. We have extended this to cover also cases where we have additional stationary design parameters or want to discover rational nonlinearities. We also have proposed an approach to denoise the measurements and simultaneously learn a dynamical model, which then goes back to a black box scheme, of course. But we could use this denoise data then with the SIMD approach, with the AKA-SIMD approach to discover the analytic equations, if you wish. This is the next step that we have also to implement, I suppose, and test. And the other thing is that we also know, it's just an idea at this moment, that from the model reduction world where many of us come from, that the solutions of PDE models often evolve in low-dimensional manifolds. This is why model reduction based on reduced basis or so on is successful. So how can we make use of that in this approach? So yeah. Okay, that's all. Thanks for your attention. And here are a few references that we have been using. In particular, this is the one preprint for related to the first part of the talk. been out for a while. The preprint is just recent. I didn't.
Okay, thank you so much, Peter.
Yeah.
That was a wonderful talk. And we do have several questions. Let's start with the question from Rob. He asked, how would this compare to the use of Levenberg Marquardt as a simple fitting technique?
Well, I cannot say that because we haven't done this comparison. I'm also not so much experienced with different techniques. Certainly something that we can that we should test in the future. Yeah. So I cannot really say anything informed here because we just haven't done any on this level.
Okay. The next question is by Fei. Can you show the effects? Can you show the effects of the denoising implicit neural network by feeding the dynamical neural network directly without it?
I'm not sure whether I understood that question, please.
Right. Fei, if you can unmute yourself and clarify your
Thanks for the
question.
great talk. So my question is, so if you just feed your noisy data with the dynamical neural network without the denoising step?
Yeah, I don't think, I mean, in that case, we would not have an easy way to use the gradient loss, I think. And that might not give as smooth results as the approach that I showed. Maybe Pavan, if I don't know whether you have done these experiments in the course of the action. Say anything here?
Pavan, if you can unmute.
Yes, I think what Peter just now said it. I think the derivative, if you don't match the derivative information, like the one derivative which you get from Runge-Kutta and also one derivative which you can get from the implicit neural network, if you don't mismatch, then there will be even more wiggles around basically. So I think this part of loss is also very important to have denoise data for if you have a large amount of noise in the data.
Mm-hmm.
Okay, next question is by Cody. Have you seen the paper on archive paper by Fiuza and Alves? They use Cindy to identify PDEs in an integral formulation from noisy PIC simulation data. In their case, denoising did not work well. I think they just tried Gaussian smoothing, but the integral formulation worked well. Can you comment on
I must admit that I have not read that paper so far, so it's hard for me to comment on that. I'm not sure whether Pavan has had a look at it, but I cannot say cannot comment on their work in that sense.
Right.
Whether this is an effect that we will observe if we go to more complicated PDE models, that's of course hard to predict, and that would be interesting to see. And I think if they we will have a look at this paper and see what kind of examples they use, and we'll try it with our approach, whether we can have to run into the same difficulties or whether we get something better. That would be definitely interesting to see.
Right. Okay, next question is by Beta. Is your RK4 Cindy approach also applicable for finding the second order dynamics?
RK4 would probably not be the right thing to do then, but there are, of course, the RK4 can be exchanged for any other integrator, basically, right? So if I would like to identify a second order dynamics, I would then go, for instance, to a leapfrog scheme or whatever, or Newmark method as the filter for this approach. Yeah, and I think that can be done. Yeah, but we haven't done that yet.
Okay, next question is by Nathaniel. He asks, the classical problem with Cindy is what happens if your operator isn't easy to guess a dictionary for a priori. You touched on this with rational functions. Have you done any experiments on your denoising strategy when the dynamics to be learned can only be approximated by the dictionary and not exactly represented?
No, this is also beyond our current experimentation, I think, unless Pavan has done anything in that regard in the last days. But yeah, I mean, of course, there's a hierarchy of difficulties, and we are very low in that hierarchy at the moment of the difficulties that you can add in the identification process. Yeah. As I said, it's the optimizing the choice of the dictionary automatically, I think this is beyond the work we have been doing, and that's, I think, an important question. And
yeah.
in order to make these approaches more successful even.
Yeah. Okay. Next question is by Anders. Nice talk. Have you tried your approach on a pure wave propagation problem?
Pure wave, not. I think it's all the Burgers is a damped wave in a sense. I think we can go to rather low viscosities with this approach in comparison to some model reduction approaches that get problems with these viscosities. I would have to think about, if you know that you have a pure transport phenomenon in your problem, I think one would also need to take this into account in the integrator that is used in the scheme. AK4 wouldn't be the choice there. But there are, of course, integrators that are designed to stably reproduce wave phenomena. And I think that would be, from the implementation side, would be more complicated. Also, probably computationally, it would get a little bit more involved. But I think that could be done. Whether it really works, I cannot say at this moment. But I would recommend using a different integrator.
Nice. Okay. Next question is from me. Is RK Cindy available as an open source code?
I think Pavan can answer that. I think it's a GitHub available code here.
Yeah, I think it's still not public. Maybe in the next weeks it will be public.
Okay, since you guys just published in the archive, right? Yeah. Okay. I would like to see the open source code once it is available in public. Okay, I do not see any more questions. Okay, so is there any other questions from audiences? No? Okay. With that, let's conclude. Thank you so much for the great talk, Peter. It was really well done. I learned a lot. So thank you so much.
Thanks to all the participants for listening and for staying until the end.
That's awesome. It's 7 o'clock in Germany, right?
Yeah. Time to have a beer.
Okay. All right. Thank you again. With that, we will conclude the seminar today, and we will see everyone in next DDPS seminar. Until then, stay safe, and see you next time. Okay. Bye-bye.
Bye-bye. Okay. Bye-bye.